Trigonometry, three-dimensional trigonometry, introduction. Lines and planes in three-dimensional trigonometry. Now, for 3D trigonometry, we assume that all lines are straight and all planes are flat surfaces, although they don't have to be horizontal. Planes can be sloping. Then we have the distance of a point from a line is the length of the perpendicular from the point to the line, as in the diagram. The distance of a point from a plane is the length of the perpendicular line from the point to the plane. Now we mean that a line is perpendicular to a plane if it's perpendicular to any line drawn on the plane. Again, as we can see in the diagram. Now, we may be interested in the angle between a plane and a line. If a line is not parallel to a plane, then it will meet it at one point, let's say P. We can then choose another point, A, on the line and drop a perpendicular from A to the plane at a point, say, B. Then, the angle between the line and the plane is the angle APB. If we have two planes that meet each other, we can find the angle between the two planes. So, if the planes are P1 and P2, as in the diagram, and they meet along a line AB, then to find the angle between the planes, we choose a point C on AB, and we draw two lines, CD and CE, so that they're both perpendicular to AB, and each of them lies on one of the two planes. Then the angle between the two planes, we can call it theta, is the angle DCE. If we were to look along the line AB, then the two planes would appear as lines, and the angle would be the angle between those two lines. Now, if we have a problem in 3D, we may be given a 3D diagram. Now this is drawn with a perspective so that you can see all three dimensions at once. However, right angles may not appear as right angles. Rectangles may not appear as rectangles. They may appear as parallelograms. So, when considering a triangle or other shape in the 3D diagram, it's always best to sketch a diagram of it laying flat, so sides and angles can be more easily identified. In the example we have here, we've got a pyramid and a triangle which is bounded by one of the edges of the pyramid, the height, and the base of the pyramid. If we look at the flat view of the triangle, it's much easier to see that the triangle has a right angle. Angles of elevation and depression. The angle of elevation of a line is the angle the line makes upwards from the horizontal. We can see that in the diagram. The angle of depression of a line is the angle the line makes downwards from the horizontal. Again, we can see that in the diagram. Let's look at an example. A flagpole 5.8 meters tall stands in the corner of a rectangular courtyard. The courtyard measures 15 meters by 19 meters. Find the angle of elevation of the top of the flagpole from the opposite corner of the courtyard. Well, to solve this, we first need to work out the length AC. To do this, we need to consider the triangle ABC. So, first let's draw a plan view of the courtyard. Now we can see that the triangle ABC is right-angled, so we can use Pythagoras' theorem. AC squared equals 15 squared plus 19 squared, which means AC squared is equal to 586, or, taking the square root of both sides, AC is equal to the square root of 586. This gives us AC is equal to 24.207. Now let's consider the triangle ACE. Again, we should draw a flat view diagram. We want to find the angle of elevation which we've marked as theta. The height of the flag, 5.8 meters, is the opposite side of the triangle, and the diagonal of the courtyard, 24.207, is the adjacent side in the triangle. Now we have that the tangent of theta is the opposite over the adjacent, so the tangent of theta is 5.8 over 24.207. If we take the inverse tangent of both sides, that gives us theta equals the inverse tangent of 5.8 over 24.207, and working that out on a calculator we get theta is equal to 13.474 degrees. So rounding it off to one decimal place, we get the angle of elevation is 13.5 degrees. Let's have a look at another example. A pyramid ABCD has a square base with sides length 8 meters. The top E of the pyramid is 3.2 meters above the center F of the base. Calculate the angle ABE. Now to solve this we need to consider the triangle ABE. Let's draw a diagram of it. Now to calculate the angle ABE, which we can label as phi, we need to draw a perpendicular from E to H on the base AB in the diagram. Then HB will be half the length of AB, so HB is 4 meters. Now to work out the length EH, we must first consider the triangle EFH. Now again, if we draw a diagram of this, we've got HF is 4 meters and EF, the height of the pyramid, is 3.2 meters. So we can use Pythagoras' theorem. HE squared equals HF squared plus EF squared. So HE squared is 4 squared plus 3.2 squared, which works out to be 26.24. If we take the square root of both sides, we get HE equals the square root of 26.24, which works out to be 5.1225. Now, if we write that in the triangle EHB in diagram 1, we have EH is 5.1225, which is the opposite side for phi, and HB is 4 meters, which is the adjacent side for phi. So the tangent of phi is the opposite over the adjacent, which is 5.1225 over 4. So taking the inverse tangent of both sides, we get phi is equal to the inverse tangent of 5.1225 over 4. And if we work that out on a calculator, we get phi is equal to 52.014 degrees, or rounding it off to one decimal place, the angle ABE is 52.0 degrees. One more example, example 3. A rectangular ski slope consists of a plane that measures 100 meters across and 60 meters down, set at an angle of 16 degrees to the horizontal as seen in the diagram. In part 1, calculate the height the top of the slope is above the base. Well, to solve part 1, consider the triangle AED. Let's draw a flat view of it. We have the angle 16 degrees, and then the side AE is the opposite side. The side AD, 60 meters, is the hypotenuse. Now we have the sine of the angle is the opposite over the hypotenuse, so sine of 16 is equal to AE over 60, or AE over 60 is the sine of 16 degrees. If we multiply both sides by 60, we get AE equals 60 sine 16. Now that gives us AE is equal to 16.538. Rounding it off to one decimal place, we get the height AE is 16.5 meters. Now in part 2, a skier starts at B and skis in a straight line to D. Find the distance travelled. Now to do this, we need to draw a plan view of the rectangle ABCD. and then we can consider the triangle BCD. Now, this is a right-angled triangle, so we can use Pythagoras' theorem. And that gives us BD squared is equal to DC squared plus CB squared. So BD squared is equal to 100 squared plus 60 squared, which is 10,000 plus 3,600, or 13,600. And if we take the square root of both sides, we calculate BD is equal to 116.619 metres. So the distance that he travels is 116.6 metres, rounded off to one decimal place. Now in part 3, we're asked to calculate the angle his track makes with the horizontal. So let's consider the triangle BDF. Again, we need to draw a diagram. We want to find the angle the track makes with the horizontal, so that's the angle theta. And opposite the angle theta, we have the side BF, which is 16.54, and the hypotenuse of the triangle is 116.62. So the sine of theta is the opposite over the hypotenuse. In other words, the sine of theta is equal to 16.54 over 116.62. If we take the inverse sine of both sides and then use a calculator, we get theta is equal to 8.1536. Now we can round that off to one decimal place, and so the angle that his track makes with the horizontal, which is the angle theta, is equal to 8.2 degrees.